Hi, and welcome to Module 5 of Digital Signal Processing. In the previous modules, we concentrated on the concept of signal. We looked at signals, we took them apart, and we put them back together. And now it's time to start addressing the second part of the story, the processing part in digital signal processing. Now, when we process a signal, we no longer simply analyze it, but we manipulate it and we transform it into another signal. There are very many ways to skin a cat, and probably even more ways to process a signal. But of all the possible ways, we're interested in the class of processing algorithms that go under the name of linear time invariant filters. Filters are simple and yet very, very powerful devices that have been around for a very long time, especially in analog electronics. And to think what a filter does, think of the knobs on your stereo with which you boost the bass or dim the treble in the music you listen to. In the digital world, filters have the added advantage that they can be implemented very simply on general-purpose architectures. This is a rather long module, since not only do we need to define the filtering paradigm, but then we also need to understand how to implement and design filters that do what we want them to do. And in spite of the length, this module only scratches the surface of the world of active signal processing. We will leave for future classes concepts like adaptive signal processing or nonlinear signal processing. But I'm sure that this module will whet your appetite with respect to everything that you can do in the world of digital signal processing. The module is structured like this. The first three sub-modules will concentrate on the concept of filter and will characterize a filter in the time domain. We will illustrate the key points using a mock problem where we try to remove noise from an otherwise smooth signal. By now we know that the time domain is always only half the picture, and so we will spend modules 5.4 and 5.10 to extend the filtering paradigm to the frequency domain. This will allow us to define a class of filters called ideal filters that represent really the best behavior filter that we can think of. Unfortunately, ideal filters turn out to be too good to be true, and so we will have to spend modules 5.6 to 5.10 to explore the kind of filters that we can implement and design in practice. At first we will try to mimic ideal filters, but the method will show its limitations very soon. So we will introduce a new tool called the Z-Transform that will allow us to explore the full range of filters that we can design and implement. Finally, to wrap it all up, we will have a very hands-on module where we will talk about real-time signal processing, and we will show you how easy it is to implement real-time guitar effects on your PC. So let's get started with module 5 and let's make the acquaintance of our new friend, the linear filter. Hi, and welcome to module 5.1 of digital signal processing, in which we will talk about linear filters. We will examine the two key properties of linear filters, which are linearity and time invariance, and then we will describe the convolution operator, which captures both mathematically and algorithmically the inner workings of a linear filter. In general, when we talk about signal processing, we imagine a situation where we have an input signal, x of n, an output signal, y of n, produced by some sort of black box here that manipulates the input into the output. We can write the relationship mathematically like so, where y of n is equal to some operator h that is applied to the input x of n. Already when we draw this block diagram, we are making assumptions on the structure of the processing device in the sense that we consider a system with a single input and a single output. We could imagine a system with multiple inputs or multiple outputs. But even with these limitations, the possibilities for what goes inside this block here are pretty much limitless, and unless we impose some structure on the kind of processing that happens into this block, we will not be able to say anything particularly meaningful about the filtering operation. So the first requirement that we impose on a filter is linearity. Linearity means that if we have two inputs and we take a linear combination of said inputs, well, the output is a linear combination of outputs that could have been obtained by filtering each sequence independently. This is actually a very reasonable requirement. For instance, take a situation where your processing device is an amplifier and you connect a guitar to your amplifier. Now, if you play one note and then you play the same note louder, you expect the amplifier to produce just a louder note. Similarly, if you play
one note and then another note, and then you play two notes together, you expect the amplifier to amplify the sum of two notes as the sum of two independent amplifications. Now note that this is not necessarily the case in all situations. For instance, in some kinds of rock music, you want to introduce some distortion, and so you add a fuzz box that will distort the signal non-linearly to create very interesting effects, but that belong to a completely different category of processing. The second requirement that we impose on the processing device is time invariance. Time invariance, in layman terms, simply means that the system will behave exactly in the same way independently of when it's switched on. Mathematically, we can say that if y of n is the output of the system when the input is x of n, well, if we put a delayed version of the input inside the system, x of n minus n0, what we get is the same output delayed by n0. And again, we can use a guitar amplifier as an example. If I turn it on today, well, I expect it to amplify the notes exactly in the same way that it amplified them yesterday. But again, some types of guitar effects exploit time variance to introduce a different flavor to the music that is being played. For instance, the wah pedal is a time-varying effect that will change the envelope of a sound in ways that are not time invariant. So what are the ingredients that go into a linear time invariant system? Well, linear ingredients. Addition, which is a linear operation, scalar multiplication, another linear operation, and delays. Another requirement that is not mandatory, but makes a lot of sense if you want to use a linear time invariant system in real time, is that the system be causal. By that we mean that the system can only have access to input and output values from the past. In that case, you can write the input-output relationship as follows. The output is a linear functional of past values of the input and past values of the output. The impulse response is the output of a filter when the input is the delta function. A fundamental result states that the impulse response fully characterizes the behavior of an LTI system. Let's see why that is so. Assume that we have a filter and we can measure its impulse response by inputting a delta function, and it turns out that the impulse response is an exponentially decaying sequence h of n equal to alpha to the power of n times the unit step. Now we want to use the same filter to filter an arbitrary sequence x of n that in this example is simply a 3-point sequence that is equal to 2 for n equal to 0, is equal to 3 for n equal to 1, and is equal to 1 for n equal to 2, and is 0 everywhere else. So we can always write our sequence as a linear combination of delayed delta function. So in particular, for our example, x of n is equal to 2 times delta of n plus 3 times delta of n minus 1 plus delta of n minus 2. Now we know the impulse response, so the response to the delta, and by exploiting linearity and time invariance, we can compute the response of the system to the input sequence x of n just by knowing the impulse response. Indeed, we apply the linear filter to the linear combination of deltas, and by exploiting linearity first, we can split the operation of the filter over the 3 components of the signal, and by exploiting time invariance, we just sum together appropriately scaled version of the impulse response delayed. We can look at this graphically, and we see that when we filter the first component, 2 times delta of n, we get 2 times h of n. The second component of the signal is 3 times delta of n minus 1, and this gives rise to 3h of n minus 1, which we plot on top of the other response. And finally, the last component is simply delta of n minus 2, which filter gives h of n minus 2. So now we have the 3 components, we sum them together by linearity, and we obtain the response of the system to our arbitrary input. In general, remember that we can always write x of n a generic discrete time sequence as the sum for k that goes from minus infinity to plus infinity of a sequence of time delayed deltas scaled by the values of the sequence itself. So this probably seemed like a futile exercise in module 3.2, but now we see the usefulness of this representation because by linearity and time invariance we can express the output as the sum from k that goes from minus infinity to plus infinity of the values of the sequence times the impulse response, time reversed and delayed by n. This sum here is so important in signal processing that it gets its own name, and it's called the convolution of sequences x of n and h of n. The convolution, which represents the output of a filter given its impulse response and an arbitrary input sequence x of n, is actually an algorithmic formula to compute the output of the filter. The ingredients are an input sequence x of m and a second sequence x of m. And the recipe involves the following steps. First, we time reverse the impulse response. So we flip it in time. If it goes like this, then it will look like this. And at each step, from minus infinity to plus infinity, we center the time reversed impulse response in the current sample n. So we shift the time reversed impulse response by minus n. And then we compute the inner product between this shifted replica of the impulse response and the input sequence. Let's look at this graphically using the same examples that we used before. So we have an impulse response, which is a decaying exponential sequence, and we have a 3-point simple input sequence. We plot these three actors on a chart like this. We have the input sequence on top. We have the time reversed and the delay impulse response on the second panel. And here we have the inner product between these two sequences. So at each step, as I said, we center the time reversed impulse response on the current sample. So we start at -4 and we compute the inner product. Since the input signal in our example is non-zero only between 0 and 2, up to 0, fundamentally nothing happens and the inner product is always 0. And we can see that it was 0 for values before -4, and it will continue to be 0 until we hit 0. At which point we start to have an overlap between these two sequences and the inner product will not be 0. In particular, on the first step, it will be equal to this sample, which is equal to 1, times this sample, which is equal to 2. So the sum will be equal to 2. We advance another step, and then we see that the overlap involves 2 points now, here and here, and we compute their products and their sum, and we get the second point in our output sequence. Third step will finally involve all 3 points from the input sequence. We compute the product with the impulse response and the sum, and we get our third output sample. And the process continues like so. Now, since the impulse response is an infinite sequence, one-sided infinite sequence, from now on, the inner product will always be non-zero, and we'll have an output that will continue to be non-zero forever and ever. Finally, a few words on the convolution. The convolution is of course linear and time invariant because it describes a linear and time invariant operation. It is also commutative, which means that if you have two filters in cascade, you can safely invert their sequence and the result will not change. For absolutely and square summable sequences, the convolution is also associative, which means that if you have a cascaded system, you can lump their effect into a single filter whose impulse response is the convolution of the individual impulse responses.